So, good morning and a very warm welcome to our first Easter School in our doctoral training center for risk and uncertainty in complex systems and environments. So we have 3 speakers this week. The whole week, the Easter School goes over the whole week. So the plan is that all the 3 speakers deliver some lectures, and then at the end on Friday, or Thursday and Friday, we have then problem sets. So it means each lecturer gives some lectures. Then we have kind of problem-solving classes, which are kind of tutorial-like. And after that, on Friday, you have opportunities to ask questions. So please don't be shy. Just put up your questions, raise your arm whenever you think. So we run the whole Easter School in a very relaxed way. So it's not like here's an expert giving you a lecture and disappears. So the whole thing is meant for interaction, so that everybody gets out really the maximum. So you should ask questions about how these methodologies can be used for your project and everything. Whatever you are interested in, where you can find literature, how it is meant, how to understand everything. So don't be shy. Just have a very, very vivid interaction with our 3 experts. So with that, I do not want to make a very long story to kill a lot of time. So today we start out already the topic of the Easter School, just to explain this, is mainly an interaction, let's say, in the intersection between mathematics, computer science, and engineering. So we talk about methods, let's say, mathematical methodologies, how to handle risk and uncertainty. We talk about, then with Professor Kruse next days, about, let's say, how to handle data, and also how to use this for optimal design with Professor Zaka. And today we have our first speaker, which is Professor Grigoriu from Cornell University, about stochastic modeling, which is, let's say, a key part for the entire CDT. So his lectures are pretty much important for the entire CDT, for everybody. To introduce him, Professor Grigoriu is, I think, one of the absolute top experts in stochastic modeling in the world. So to read his whole CV, I think would kill 2 hours. So I just make it short. So Professor Grigoriu is our top expert for stochastic modeling from Cornell University. So please feel free to contact him. He has a huge knowledge in the intersection between mathematics and engineering, and I'm sure he can explain really everything on every question which comes up.
Well, I don't know if I can explain everything, but I can explain some things, and I hope during this, thank you very much, Mike. I hope during this lecture you'll feel free to interrupt me anytime when you do not understand. So it's going to be a feedback system. It's not just one-way traffic. So there's no reason to sit there and to think, well, I'm the only one that didn't understand that. Most likely I didn't explain it clearly, and this is why I didn't understand. So please feel free to start me and say, well, clarify that thing. It is really a pleasure to be here to try to help, and I really thank Michael for this invitation to spend some time with you. And as he already mentioned, our main objective today is to construct tools to estimate the characteristic of outputs of system with uncertain properties. So the general scheme we are going to discuss today is the following. We consider a system with uncertain properties. And the input to this system is random. Can you read up there, or you want me to write? It's okay? And of course, this system has a certain quantity of interest, a certain output. And we want to characterize this probabilistically. To do that, we have to construct a certain framework. And that's the probabilistic framework we are going to talk about today. Let me just give you an example to clarify this idea. This is a trivial example, but all of these examples are very useful. Suppose the system is this cantilever, and the stiffness is random. So this is system properties. You don't know the stiffness precisely. You know it in a probabilistic setting. And the load, it's also random. And the output of interest is a deformation at the tip of the cantilever. And let's call it y. So if the span of this cantilever itself, y, I think, has this formula. Okay? So the setting is the following. Stiffness is random, k. Force, the input, is random. Therefore, y, the output, is also a random quantity. In the deterministic world, the design condition, it's simple like that. You require the y, the output. In the deterministic world, it's a number. Has to be smaller than a critical quantity, whatever that critical quantity is. In the probabilistic world, you cannot satisfy this inequality precisely unless in special conditions. So in the probabilistic world, we have to restate this in a different way. We have to simply ask that the probability that this is true is larger than a critical value, exceed a critical probability, which is called a certain limit reliability. So this is a setting we are going to discuss today. And in order to satisfy this condition in a stochastic probabilistic setting, we have to understand how to calculate this thing. So this is the objective, our objective today, to construct tools to do these calculations. Okay? So everybody is on the same page with this, is clear where we are? All right. Now, to do this, we need to construct a certain framework. As we did in any undergraduate in elementary school, you have to learn how 1 plus 1, what's the meaning of 1 plus 1, for example. We need a framework here. And the framework for this setting, it's a probability, the probabilistic framework. It's a probability space. And the probability space has three ingredients. Please, if you cannot read or cannot hear me, don't sit there and suffer. Let me know. Has two elements, which I'm going to define and illustrate one by one. Sample space, sigma field, this is a calligraphic F, and probability measure. So I'm going to go one by one and tell you what they are. If I'm going too slow with this concept, let me know and I accelerate it, okay? It never happened to me, anybody. Anytime when I ask the class, shall I accelerate, nobody will say anything, even they know it precisely. But I hope every time, I hope it's different. But obviously it's not. Sample space. Sample space contains all the possible outcomes of an experiment. Example. If you toss a coin, the possible outcomes is tail and head. We assume that it cannot land on the edge and sit there, right? These are the only options. If you roll a die, you can see 1, 2, 3, 4, 5, 6. These two sample spaces have something in common, are finite. They have a finite number of elements. On the other hand, if you go to a laboratory and test concrete cubes, for example, for each cube you are going to get a certain strength. It's going to be a set of continuous numbers in a certain range. So for that experiment, omega would be a certain interval, a, b, of the real line, which is finite. But of course, a number, any interval of the real line, it's an uncountable set. So these are finite sample sets, and this is an infinite sample set. Okay? So we're done with the first component of the probability space. This is so-called sigma field. It consists of all relevant outcomes of an experiment. And I'm going to give you a definition, but this is an intuitive definition. So are the relevant outcomes of an experiment. Example. Think of the following game. We roll a die. And if the outcome of that experiment, it's 1, 2. I'm just making it up right now. If you see 1 or 2, you are going to win $10 or pounds, depending on the place in the world. On the other hand, if it comes 3, 4, 5, and 6, you are going to lose $5. Now, in this game, whether it's 1 or 2, it's irrelevant. All you need to see if the outcome is in here or in here. That defines the game. So these are the relevant outcomes of this experiment. You don't care whether it's 3, 4, or 5. Only if it's the outcome, it's within this set or within this set, that defines the game. If I change the game, and I say, okay, I keep this as it is, but if it's this, you are going to lose $3, $4, $5, $6, for example. If this representation is too coarse to describe this experiment. Now, what the sigma field does, as I said, it includes all relevant experiment, and I should say and has a certain structure. And this is a structure which is required. And now I'll give you a definition. So F is a sigma field on omega. And we know what omega is, right? If satisfies 3 conditions. This is an empty set. Number 2, if A is a relevant event. So again, think of F as a set of relevant events. Then the complement of A, that is A does not happen, it means a complement. It's also an event. Now, this is rather intuitive, because if you observe A, for example, you know that the complement of A has not occurred. Right? Shall I say it again, or it's obvious? If this is A, if you observe A, that is, the outcome is either 1 or 2, you know that the complement of A, which is this, cannot occur. And the other property is that if you have a set of such events where I, is the index, belongs to a set I, which is countable. What that means, countable? You can put that is a one-to-one correspondence between I and a natural number. That is, you can say, I have A1, A2, A3. The interval 0, 1 of the real of the real line is not countable. It's uncountable. Okay? Countable. That implies that the union, it's also in F. Okay? So I claim that this is also an intuitive properties. That if you observe A1, for example, if this is A1 and this is A2, if you observe A1, you observe also the union of A1 and A2. Because it's one or the other, it's not and. Okay? intersection its end. And finally, the probability measure. I'm going to put a star and move somewhere here to define it. P is a probability measure. And this is a function defined on the set of events, that is a sigma field, it is a set of events which is relevant to an experiment, with value in 0, 1. Yeah, you hear the weatherman, although you don't believe it, that the probability of rain tomorrow is 80%, and you may see sunshine, but it's between 0 and 1. And has the following properties. The probability of seeing the empty set is 0. That is, you don't see anything. The other is the probability of the union I 1 to infinity. Whoops. AI is the sum and provided AI, it's a partition. And I'm going to draw a picture of omega. Okay? So what means is a partition? So let's stay for a moment because I'm going to use this word several times. If this is omega, that is a sample space, a partition of it, think of this like, pizza, and you cut slices of the pizza. If this is your slice, you divide the pizza in all kinds of slices. They have nothing in common. So they are disjoint. That is, the intersection of two different slices is 0. And the union of all is the whole pizza. Okay? That means a partition. And finally, probability that you are going to see an event, regardless of what event you're talking about, it's unity, because once you do the experiment, you are going to see something. Okay, so this is a technical condition, but these two are rather intuitive. If you go to the pizza example, if you draw at random two slices with the probability of seeing slide 2 and 3, it's the sum of these two probabilities. This is what that thing says. Okay? So let's summarize where we are and begin to use these concepts. So again, it's important, if it's something not clear at this stage, please let me know, and I try to use some other example also to clarify. So we're saying that the framework of probabilistic calculations is this probability space, which has 3 ingredients. The sample space collects all the outcomes of the experiment, and we had some examples. The sigma field is a collection of relevant experiments with some structure, which is defined here. Any member of F is called an event. This is an event, this is an event. And then we have this measure which tells us how likely something to happen is, which is called the probability measure. And it's that function on the sigma field with value 0, 1, which has some properties. The first one I said it's a technical property, the other two are rather intuitive. Okay? So we said, guys, is this? Okay. So now let's try to use some of this stuff. Maybe I'm going to tell you one more thing, if you can solo one more technical thing. And then things are going to be much more applied, but we needed this framework at this time. A, it's an R. Can you read that lower? I have to write. You can read, okay. A, it's a collection of subsets of omega. Okay. So it would be a task for us this afternoon to show something very small. That if I take the, still can read here, or it's getting hard? Okay. If we're looking at this, the intersection, you cannot see here, right? Okay, I'm going to move here. So we are looking at this intersection. These are sigma fields with the following property, that G, this sigma field, includes A. Okay? So again, sigma field, G, it's a sigma field. And the only requirement has that it's larger than our set A we started from. So what I'm claiming, and we are going to show this afternoon, that what you get, it's a sigma field, and we are going to denote it by this, sigma of A, to indicate that it's a sigma field generated by A. So it's simply called this way. Okay? So how do you think we are going to show that's true? We are going to show this afternoon in 2-3 minutes, but I don't want to interrupt the flow right now. Well, we have to check that it satisfies these conditions. Right? If it satisfies this condition, it's a sigma field. We're done. And the thing is, it's the smallest sigma field you can construct on the top of A. And why this is relevant? It's relevant to define random variables, random vectors, random functions. Okay? So a special case of this A simply are intervals of, everybody knows what RD is? Okay. If D is equal to 1, it's a real line. If D equal to 2, it's a two-dimensional space. I'm walking here on a two-dimensional space. And this is a three-dimensional space, so if I had move my head, that would have different coordinates in R3. Okay? So if A is this interval, then sigma is called the Borel sigma's field. B-O-R-L. Let me write it clear so you can see it. Okay. Let's try to use some of these properties for calculations. So I'm going to write down a few formulas which are very useful for calculations, and prove them by pictures rather than formulas. Okay? I think you may like them better that way. So I'm going to write this list of formulas, and then, I guess with your help, I'm going to prove them. So here's a list of formulae we want to look at. So let's go one by one. Is the proof already written on the board? Let me draw a picture. So I'm talking the first formula. This is omega. If this is A, this is a complement of A. So A is a complement partition omega. So what's written here? P of A plus P of A complement is equal to 1. So we're done, right? What about the second one? Let's draw another picture. Again, this is omega. Which one is bigger? A. B is bigger. This is B, and A is included in B. Right? So then you can think of the probability of B. I'm trying to do it just with picture. If it's not clear, I can write more. But B is made of A plus what's left over, right? So the event B, it's A plus B minus A. So to the probability of A, you add another probability, which is between 0 and 1. So clearly satisfies this inequality. Okay, good with everybody? Okay. What about this? Let's try to do this in the afternoon, because this I need to write a couple of formulas. Okay, so we're going to do it in the afternoon. What about the last one? Well, let's draw another picture. We almost have it on the board, but not completely. This is omega. AI is a partition of omega, right? That is oh, it was a picture there, but it's gone. So this is AI, partition omega. So this is one of the member of AI. And B, it's another event. So it's something like this. This is B. So what is this piece here? Is a part of B common with AI? Okay. Then B is made of the following. Of all these small pieces. That is this piece, this piece, this piece, the union of them. And they are disjoint. Therefore, probability of disjoint events is the sum of the probability of these events. So this was written there, right? Okay. We fine? Okay. Conditional probability. That's what I have now here. I have to check, yeah. A very important concept. The idea is the following. B, when I write this, B is in the sigma field. That is, I'm writing in words, is B is an event. This is what it means. With the following property, that this probability is strictly positive. And we ask the following question. given that B has occurred, I tell you that in advance. Like, given that today is sunshine, I ask you, what's the temperature? Is between, I don't know, 10 and 20 degrees or higher. But I tell you it's sunshine. That's B. That's happened. So the idea of conditional probability is essentially to restrict the space from omega, the entire set of events or outcomes, to something smaller, which is just B. You know that that happened. So for an event A, the probability of A, and we write it this way, conditional on B. So in words, it's the probability of event A given that B has occurred. Is defined in this way. So now you realize what I'm requiring, that the probability of B has to be strictly positive. Right? Otherwise, you divide something by 0. It's not going to be 0 and 1. Now, the first thing, please note that conditional probability is a probability measure. Okay. In fact, it's a probability measure on a restricted space, which instead of omega is B. So what we have to show that is a probability measure? That it satisfies these three conditions, right? The first one, if A is an empty set, you have 0, here is 0, right? The second one, you remember the De Morgan formulas? When you, De Morgan formula gives you the answer. The third one, if instead of A you put omega, you have the intersection of omega with B, the probability of B 1 by 1, P by B by PB, it's 1, right? So done. So that's very important to know. Conditional probability is a probability. And now I'm looking at the sequence of things I have here. Okay, let's have an example with this conditional probability. And this is a very useful concept in applications. And I think one of the other presenter is going to use such concepts. So this is why I'm spending some time on it. So example. Again, the experiment of rolling a die, and consider the following events. A, it's 1, 2, 3. That is the outcome of the experiment is 1, 2, or 3. B, 2, 3, 4, and 5. And I don't know why I put some other event here. Okay, let's do this 2, 3, okay. And C, okay, we are going to use some of the events later on, 2, 3, and 4. So the question is to find the probability of A given C. Okay? So you can ignore this B event at this time. I'm going to use it later on. So you can calculate it in two ways, by formula and by intuition. So let's do it by formula. I'm copying this formula here, right? Okay, A intersection with C. The intersection of A with C is 2 and 3. So it's 2 out of 6. And C, you see if 2, 3, or 4 occurs. So it's 3 out of 6. So it's 2 by 3, right? By formula. And by intuition, if you want to call it this way. So think of the meaning of conditional probability. C has occurred. That's it. You know that it's one of these 2 numbers, 2, 3, or 4. Given that, what's the chance of seeing A? Is 2 options out of 3. So you get directly that. C has occurred. So if C has occurred, you are going to see A if you see 2 or 3. If you see 1, you don't see A. All right. 2 important properties which involved these conditional probabilities. Law of total probability and Bayes formula. I see you don't ask any questions. So how shall I? Am I going too slow? Shall I accelerate a little bit, guys? Come on, help me a bit.
Can I ask you a question?
Go ahead.
I'm confused between the sample space and sigma field.
Right.
The sample space, you have tail kind or 1, 2, 3. But sigma field seem to have, you mentioned the example is the outcome. If 1, 2 is $5 and $10. And then over here on the left, it seems to say that A is sample space, but also is sigma field.
Okay, on the left, where shall I go on the left? You mean this left or which left?
You see, A is sample space, right?
No, A is not.
In the omega sample space.
Okay, so the sample space consists of all the outcome of an experiment, whatever can happen. In the die, rolling die, it's 1, 2, 3, 4. Now, so this is omega. For the die experiment, this omega is 1, 2, 3, 4. Right? 5, 6. A, it's a subset of omega. A, it's a subset of omega. It may or may not be an event, depending on the definition of your sigma field. What sigma field? Consists of all subsets of omega, which are relevant to you. For example, in the experiment of structural reliability, there are 2 events relevant. The structure survives or fails. So you divide the sample space, which can be, let's say, in the experiment of that cantilever, we're looking at the outcome. The outcome was a displacement at the tip of the cantilever. Let's say the critical value is 1. Any displacement smaller than 1, an infinite number of outcomes, it gives you safety. If it's larger, it's failure. So the sigma field would consist of the following sets: from minus infinity up to 1, from 1 up to plus infinity, and the union of them.
Then in this example, sigma field doesn't seem to come into play.
In which example?
Or here.
Here?
Yeah.
Well, you cannot calculate, if you remember the probability. Probability is defined on sigma fields, on member of the sigma field.
Without knowing whether, the concept sigma field doesn't seem to be involved when you calculate those probabilities.
Here?
Yeah.
Well, the probability measure I'm using here is the following. That the probability of any outcome in this particular experiment I'm talking, it's equal to 1 over 6. That's the probability measure. And when I'm calculating the probability of A, when I say that probability of A is 2 or 1 out of 6 or 3 out of 6, I'm using the definition of the probability measure, which is on the sigma field. Okay, why don't we talk a bit later in the afternoon, because then we go too much. But this, I think, if somebody else has a similar confusion, omega, the sample space, includes everything you can see in an experiment. The sigma field, it's just subsets of possibilities. Like this is a possibility. You are not going to see when you roll a die 1, 2, 3. You are going to see one of them. So this is a collection of possible outcomes which are relevant to you for some reason. So that the sigma field is. This type of collection. And depending on the objective, you may use different sigma field. In the reliability problem I just mentioned with that cantilever, the sigma field consists of all outcomes with displacement smaller than 1, larger than 1, the entire real line, and the empty set. That's what you need. If you need something else, that is, if its displacement is in this range, you have this degradation, if this range, a different degradation, you need a much finer sigma field than what I defined. And the probability has to be defined accordingly. Okay, but let's talk more in the afternoon about that. All right. Any other question? But it has to be short question, because otherwise we keep the long question for the afternoon. Okay. So we are saying we try to do this law of large number and base formula. Oh, I said the law of large number? Yeah. No, but I didn't mean that. Okay. So let me first define it, and then I tell you what it is. We already did it to some respect. So we have a partition of omega. Again, think of this partition. Omega is the entire pizza. AI are slices of a pizza. Okay. And B is an event. Again, an event doesn't have to be a single outcome. If you roll the die, a single outcome, it's 1, 2, 3, 4, 5, 6. A is not something, a single outcome can be 1, 2, 3, 1, 2, the whole thing, and so on. So it's a big difference between single outcome and events. Events can be single outcome, but the otherwise not true. And I think we had a picture, which is this picture here. And we have a formula, which is this formula here. So I'm going to combine this formula with conditional probability to obtain another formula. Okay? So we already know by that property, I think it's the last one written here, that this is true. So now we are going to use the concept of conditional probability. That is, this intersection can be written the product of conditional probability and what's at the bottom here. Okay? So let's write it this way. Let's make sure it works. What's this? Conditional probability. Probability of B intersection AI divided by probability of AI. Constant, we have it. So now base formula, which is something quite similar. So we are going to have exactly the same setting, and I'm going to give you an example right away. That is, the setting is from here, AI partition, if B is an event. So this is how we are going to write it. So this is a definition of conditional probability. I just copy the definition from here. And now I'm going to use for PB the expression written here. Yeah? So anybody wants to tell me what shall I write? What shall I write in place of this? That representation, it's a law of total probability. So let's write it. Yeah.
I think the numerator should be AI intersection B on the second.
Thank you very much. Thank you. Yeah, I was looking, didn't work quite right. Thank you very much. Okay. But I can do something, and instead of this, let's write something different.
Sorry, I'm in the middle one, where you've got probability of AI given B.
Oh, yeah. And the same thing with the other one. Yeah, both of them, right. Yeah. Okay, thank you. And let's write this also in the same format. So instead of this, what can I write? Okay? Again, using the definition of conditional probability. So basically, I just placed some formula so far. But what's important is the interpretation of this formula. So this is the interpretation we have here. Think of B as an observation. We observe something, whatever, a temperature in a certain area for a certain time interval. And we want to design a heating system for a particular building. Right? So we start from some initial belief in these events, which can be the temperature is smaller than 10, between 10 and 20, 30 and 40, and so forth. So this is the probability of these possibilities, which partition the outcomes of a particular experiment, in this case, the temperature in Liverpool, for example. So this is our prior knowledge. But then we perform some experiments B. And then we want to adjust our knowledge as a function of what we see under some condition. That is, if the temperature is between 10 and 20, we observe that we feel comfortable or not, or whatever the case is. And I'm going to give you immediately some numbers. So this is a prior distribution on all possible events. In our case, temperature in that particular case. And what's the output of the formula? Given some observation, which is B, we want to update our knowledge on the probability of these outcomes, AJ. So we start from some prior. We perform some experiments B, and we end up with a posterior probability of the events of interest. In the afternoon, we are going to do something like this in the setting of distributions. We try to update some parameter of a distribution based on some observations. But let me give you here a trivial example of how this works, and to clarify this concept. So these are the numbers I have here. So the prior P1 and Now, any surprise that, so in this case, our partition of the sample space is in two, right? A1 and A2. So one is a complement of the other. Any surprise that one is 0.8 and the other is 0.2? Or it should be, if I, instead of 0.2, I write 0.1, anybody would object? I think so, right? Okay. And then the probability of event B, given we observe A1. This comes from experiments. It's, I said, I just made up some numbers. This I took it to be 0.7. Okay. All right. So we can think, for example, that B is a reliability of the system under earthquakes, if A1 is the event of earthquake, and B is a reliability of the same system under extreme wind. So our sample space consists of two options, two environmental extreme events, earthquake and wind. And of course we are interested in two things, global reliability of the system B, irrespective whether it's earthquake or wind. And also we want to update our initial assessment of the environmental conditions based on some observation. So the overall reliability under earthquake and wind is here, right? That is and the same term in A2. And the posterior probability of earthquake and wind come from the base formula. Okay. So I think you can try to fill in the numbers, and if it's not clear, we can look them over in the afternoon. All right. No, do you think we should make a small break? Guys, it's fine with me to continue. If you need a short break, like 5-10 minutes, we can do that. So what do you prefer? Break, of course. But let's keep it short, all right? Okay, so like 5-10 minutes. The upper bound is 10 minutes.